Hello everyone, my name is Qazi Tahsin Mahmood. I am a graduate student at the Department of Mechanical Engineering at Wayne State University. Today I will be talking about the elastic beats in a granular matter materials, which is a quantum inspired framework for a reverse topological and quantum computational model. So in the current revolution of the like data transfer and computational by high speed data transfer and computational process, the quantum information processing is one of the crucial part of this. A quantum bit is the main part of the quantum information processing system, and a quantum bit is can exist in a quantum mechanical system that has a superposition. A superposition of a state is a distinct state with a specific connection, quantitative connection that can be formed by the forward superposition of the pure states, and there is a capacity to correlate between this superposition of states by learning about the analogy of the entanglement, which is a very powerful tool for the information processing. And there is a one of the sector of the quantum information processing and quantum system is the geometric and Berry phase, which can play a very pivotal role in classical and quantum mechanics, which offers a very deep insight in the essence of the physical system. Berry phase is the net phase that is accumulated over a cycle when the system is subjected to a cyclic adiabatic process. And in our case we are representing the our system in with a elastic bit, which is a classical system that can create superposition of states, which is the decoherence free, because in the previous models with the quantum bit, it is susceptible to the noises of the environment, and it requires cryogenic temperatures to maintain its superposition for a smaller period of time. So our elastic bit is a classical system that is decoherence free, and is can be worked in a, usually work in a room environment, and room temperatures also. And this topological structures through Veriface enables a decoherent resistant one-way transformation system, information transmission system for us. So our motivation of the work is that there is a gap remains in the understanding the geometric and Berry-phase in a classical counterparts of the qubits, like elastic bit and phase bits. There are some study has been done in the case of the geometric and Berry-phase in the case of qubits, and studies have explored this topology and geometric phase in a elastic oscillation, vibration, and wave similar like a two, but there is similar research in the classical two-level system is there is some lacking over there. So and we study our our geometric phase and Berry phase in a granular system, because granular system are highly notable for notable for their highly adaptable dynamics, which ranges from strongly to weakly nonlinear and even linear. There is a single point contact in between the granular system which can affect the nonlinearity of the system. We will show that we can manipulate this nonlinearity to create some Berry phase in a classical model through the superposition of a state of the of those granular systems vibration. And over here we show theoretical and experimental demonstrate the control accumulation of the geometric and Berry phase in an elastic bit, and we will show that we can control this geometric and Berry phase in both time independent system and also time dependent system. So a coupled granular system is a nonlinear system that is developed by the theory of the granular bits, which is they're very highly nonlinear due to their Hertz type single point contact in between the bits. So in the left you can see that these are the two spherical balls, that is our granular bits, which is connected with each other. This is a schematic of our system where we can show that when we are connecting both of the granular bits in together, there is a nonlinear coupling that is present in between the single point contact in between the granules, and we can drive it from the both of the drive the system in both of the granules, or even we don't we can drive the system in one of the granules. This is the experimental setup that we are using for driving our system. So over here we can see that there are two granular bits that are connected with each other, and there are two transducers that is holding the granular bits. One of the transducer is driving the system, another one is reference recording. This is for our convenience, and also in the case it is possible to create nonlinearity just by driving one of the granules. We don't need to drive both of them, but for our reference point we are calculating using one of the transducer, and we are recording the displacement of the granules through two top transducer. We are using the Poisson effect to record the response of the transducer in the of the granules. So, and the general mathematical expression for the nonlinear dynamics can we can write it as this one. There's a like this is a nonlinear equation, and the general so over here there are a lot of the variables that we are using, which the granular beads have their own mass u1 and u2 at the displacement that is coming from the that is from the displacement from the equilibrium. F1, F2 and omega d represent the amplitude of the external and frequency of the external excitation. We can control this with our system that we are using a function generator to drive the system. We control these three parameters from like which and show those superposition of states that we will discuss later. And KNL is a nonlinear coupling stiffness in between the granules, and it has a damping that is coming from the environment from the contact point, like, and it can smooth out our record of the granules. And this delta knot is the static overlap that is created in between the granules and also with the wall, that we are giving some pressure from both of the side. So this is we are applying some static loads which simulates the pre-compression of the system. This pre-compression is necessary to manipulate our uh, manipulate our a non-linear system and linear system. We can by changing this delta knot value, we can make it from highly non-linear to weakly non-linear and even linearized system. So in our nonlinear system equation, we develop this equation, we apply a Taylor series expansion, and then we divide the displacement term in different orders: zeroth order, second, first order, second order, third order. So on these terms, this is for to create a theoretical model for our granular bits system. I'm not going into the detail of the all of the equations that we have, like derivation that we have, but here is we are applying the Taylor series expansion in the main equation, and this is the equation expanded equation that we can find over here. KL, K2, K3 are this term, which is the stiffness of this term. We can control the linearity and non-linearity from this stiffness term. If we increase the delta naught to a very high value, then the first term is much higher than the second and third term. So this system becomes linearized. So we at first we'll discuss about the linearized system. So this is a linearized coupled granular system where we can to in order to solve the equation, we can assume a answer of the system as u1 equal to a1 exponential I omega dt, and so on u2. Why we choose this type of equation? Because as it is a driven system, for after sometimes the particular solution only remains, the homogeneous part usually does not have effect after some time. So we apply this u1 and like answers equation, and we after stabilizing it, then we analyze our system. And from here the stiffness matrix that we can find over here, this stiffness matrix is necessary to calculate the natural frequency of our coupled granular system. So over here we can see omega d square and omega d 0 and omega d square 02. This is our two natural frequency that we are getting from the math. And in the left animation in the top plot, you can see one of the mass is moving in the same direction, and in the second part one of the two mass is moving in the out of phase direction. So we are using this as our basis state. As you know, in a case of a quantum bit, we have basis state of 0 1 and 1 0, but in our case we are using these vibrational modes, that both of them going in the same direction, both of them going in the opposite direction, as our pure states, and these are also our eigenmodes like E1 1 1 and E2 as 1 minus 1. These are the amplitudal response that we have, whether we can find from the directly from the equation A1 and A2. Now we'll show how this E1 and E2 we can derive from the our stiffness matrix. So let's say in the left you can see, if we apply E1 as 1 1 like in the equation, or we can apply the natural mode frequency in the stiffness matrix, we can get the same amount of amplitude. We not know that when a system is vibrating at their vibrating at their eigenmode frequency, these have the highest amount of amplitude. So if we drive the system very close to the our first eigenmode frequency omega d square equal to kl by m, then we can get this amplitude which they are for a1 equal to a20. That means they are moving in the same direction with the same amount of amplitude. And in the this is our in phase eigenmode, as they are moving in the same direction, which is e1 and equal to 1 1. And in the second, if we drive it in the second drive it in the second eigenmode frequency omega t a square 0 2 equal to 3 k l by m, then we can see that they are moving in the out of phase. That means a10 equal to minus a20. This is our out of phase mode, opposite direction moving. So this is e2 as 1 minus 1. So we apply this Dirac notation. That's because of this is an analogy of the quantum system. We are implementing our classical system in a quantum mechanical system, and for this is Dirac notation is necessary for the analogy with the quantum system with for vectors, and we apply it to the elasticity states of the system by writing vector in the state space. Now this is the most important part. We are implementing our classical granular models vibrational model into the uh, quantum superposition of states model. So using this complex amplitude, we have the a1 and a2. We can get the linearized eigenstates e1 and e2, and then we use the displacement field of the beads in the presence of the external excitation, and we can write the equation displacement equation of motion in this term. So we have a1 a2, which is the amplitude of the granules, omega d is the driving frequency, alpha and beta are the coefficient of the superposition of state. That means at each of the time how much e1 and e2 is retaining in the in the system. So if we see this schematic, so we can see that uh, so this is one of the system where if we have alpha equal to 1 and beta equal to 0, that means that system is E1. In the animation, if you see when we are close to E1, that means it is one of the pure states. So when we are driving the system at the first eigenmode frequency, then system is vibrating at the in phase mode. That means that the superposition of a state at that time is pure state, which is in that case alpha will be 1 and beta will be 0. This one will be E1. And when alpha is equal to 0 and beta equals 1, that means in the bottom position we can have like E2 state. The system is vibrating at the out of phase motion. So this is our pure state E2 1 minus 1, and this two level system represent an elastic bit, and this is a we can quantum analogous to the qubit. So in but the good thing as a quantum system for a qubit, we can see over there that the system is can vibrate in between 0 and 1 also. Alpha can have from 0 to 1 any value, beta can have 0 to 1 any value. So we can have a combination of both of this e1 and e2 state in the system just through the vibration of the system a1 a2 and omega t. We can control this whole system, whole superposition of states at different at different probability amplitudes. To represent any kind of qubit, the scientists and use usually the Bloch sphere. So we want to also implement our elastic beat in the Bloch sphere. So we have the equation of motion and alpha beta, and from there for a Bloch sphere component we need a theta as polar angle and phi and as an azimuthal angle in the system. So after some derivation of the math, we can get this polar angle and azimuthal angle as this one. So what is a Bloch sphere? If you want to see the Bloch sphere, we can implement our displacement field as this one, where cosine theta by 2 exponential phi sine theta by 2. Theta is the polar angle, phi is the azimuthal angle. So if we see as a Bloch sphere, we can put a superposition of states at any position. This is one of the position. So in this position, the theta means that how much it is creating an angle in between the two pair states, and phi represent that how much rotation of the angle in one rotation of the superposition of states occurs at the plane of the linear superposition of states. So when theta is equal to 0, the system is at pure state e1 1 1, and when theta is equal to pi, system is out of phase e2 1 minus 1. So we will represent our elastic beat of in this system. This is our main equation of motion for a linear model, and our driving force is F1. Like we are creating keeping the frequency as same over here, but we are changing the F1 and F2. So F1 and in this case F1 and F2 we have the epsilon and z variable. Epsilon is the state ratio that is controlling the driving mode of the system. So when epsilon is 1, the system is moving at in phase. When like driving mode is in phase, and when epsilon is 0, the driving mode is out of phase. And z is the initial phase of the driver. That means how much phase difference we are creating in between the driver. So we can with our elastic bead we can create two cases where we can fix our z and vary the epsilon. In that case our uh, uh, polar angle will be fixed, and but the azimuthal polar angle will vary, but azimuthal angle will be fixed. So this is the case, as you can see. So we can have different uh, like initial phase in the driver, and we can change the polar angle from e1 to e1 state to e2 state in this case. And in another case we can change the like our azimuthal angle, where we are fixing the state ratio and varying the initial phase. So in this case we are fixing the state ratio to zero point 0.5 and varying the is she from minus pi to plus pi. So we can, if we have an elastic bead, we can also apply some of the quantum analogous logical gate. So why we need a logical gate? To do some software based operation, because at previously I was showing all of the hardware component, but right now we are showing some like software. If we want to do some data processing, information storing, we need to apply the logical gates. So there are total 6 number of logical gates in case of a quantum system. So this in our elastic bit with the result that I have shown before, we can show all of the 6 gates. So first one is a Pauli X gate, which which can move change the pure state E1 to E2. So so it can move from E1 to E2 and E2 back to E1. Then we have Pauli Y gate, which applies which can also change the E1 state to E2 and E2 state to E1, but there it applies a bit flip and phase flip simultaneously. So it has another direction of changing the bits from E1 to E1 to E2 and E2 to E1. And we have the Hadamard gate, which can fundamental quantity that places an qubit into an equal superposition of the basis states. So it moves from takes the pure state and moves it to the like a linear superposition of states, and vice versa also. Then we have some other gates, like another three gates which applies on the linear superposition of states, which is the family of the phase gate. There are total three phase gate components: Pauli zip, S, and T gate. So we can show all of these gates. So this is our Pauli Z gate, which moves one superposition of linear superposition states to another, applies a pi phase. Another one is the S gate, which applies a pi by 2 phase, and another one is the T gate, which applies a pi by 4 gate. And right now we have to understand the Berry phase of the elastic bit. The Berry phase represents the total phase that is gained by the unit vector across the manifold for a closed path. So we, in our system, we have the driving frequency and state ratio that we are changing. We are also changing the initial phase. In this case, in our current study, we are changing the driving frequency and state ratio, and for each of this component we are moving the initial phase from minus pi to plus pi. So this is the representation of the elastic beat on a Bloch sphere, and which are defining the Berry phase of the relation as with the polar angle and azimuthal angle. So this is the equation that we had, and this is the driver equation that we have. Then we have the Berry phase that we can see. So this is the combination of all of the Berry phases from at different frequencies at different state ratio, and each of the point has initial phase from minus pi to plus pi, which is we are revolving. Then we are calculating the Berry phase. So we have two of the position. One is the trivial Berry phase, which is the value of 0, and another one is the non-trivial Berry phase, which is value of pi. We can get different responses, but what does this Berry phase means in terms of the system dynamics? So here we can see a dynamic system over here. So when the system Berry phase of is 0, in that case the like the mass at the different initial phases, both of them has the same amount of like amount of energy. So they are vibrating at the same amplitude, at they have the same amount of energy. but if we start to increase the Berry phase, and then the energy starts to localize at two of the masses. So at Berry phase of pi, then the mass is the energy is localized at each of the masses at each different position of initial phase. So initial phase of the driver. Then again it starts to go to back to zero of the Berry phase. Then again the energy distributes among the both of the masses, as we can see over here. So, and what about the phase difference of two of the masses and one of the mass with the one of the driver? So we can see a topological transition point over here, as you can see that phase difference between the masses is reverse of the phase difference between the mass and driver. So at 0.5 there is a topological transition point that is occurring on this one. Then we move to the nonlinear model. So in our nonlinear model, we can equate the coefficient of the order of stiffness. We have done a lot of math over here. Just some basic mathematical equation. We take till second order, zeroth order, first order, and second order. And using the method of undetermined coefficient, this is our equation, vibration motion for the masses at different at amplitudes. There is a lot of math over here. I am not putting all of the math. This is the basic equation that we are using. And with the over here we can show this elastic bit form change in the with respect to time. In this case we are not changing any kind of driver over here. We are driving it at a single frequency, single amplitude. Time is creating this change in the region of the Bloch sphere. Time is exploring the region of the superposition of state through of that elastic bit, and we can have different region of those change of the elastic bit at different locations by changing at different frequency. So these three Bloch sphere represent different frequency, but they with a single frequency. Each of the components represent a single frequency. The time is revolving the superposition of states in the Bloch sphere. Then we can have the Berry phase formulation. At first I was showing the Berry phase formulation with respect to changing the frequency of the driver, changing the state ratio of the driver, but over here time is changing the Berry phase of the system. Time is accommodating the Berry phase in the system with the Berry curvature connection and the Berry phase over here. So we can we can show this theoretical and experimental Berry phase in both of the cases. In the left, this is the analogy of the theoretical calculation with this second or till second order vibration of u1 and u1 u2 throughout the masses. In the right, this is an comparison of the experiment with the theory. We can see a very good match, and the ratio of the non-trivial Berry phase to trivial Berry phase is ratio comparison is very low. They are very much close to each other in the case of experiment and theory. So in my research, I have shown the studied the investigated the Berry phase in a classical system which draws parallel to the quantum models, and like quantum beats, classical elastic beam can transform analogous to quantum gets manipulated in the Bloch sphere, and the Berry phase can be varied depending on the parameter of the external drivers, and also external drivers also through the time with time independent, time dependent both model. And studying this topological characteristic of the elastic bead via Berry phase calculation could lead to very innovative development of the material science. These are some of the relevant references from our study that you can see. Thank you.